So the last thing I want to talk about is another way of thinking about the cross ratio, not just as a number, but as a function. So in particular, by fixing B, C, and D on the x-axis and letting a fourth point x vary along the axis, we can think of the cross ratio xcbd as a function of x. And the natural question is, what is that function? What is it calculating? What is it telling us? So let's look at a special case first. Let's let b equal 0, c equal 1, and d equal infinity. So b is 0, c is 1, and d is infinity. And in this case, if I just write out the definition, xcbd, the cross ratio, is xb over bc all over xd over dc. What is that equal to? Well, xb is just 0 minus x, that's negative x. bc is 1, bc is just 1 minus 0. That's over xd, that's d minus x. I won't write the infinity yet, but rather I'll take a limit in a second. And finally, dc is 1 minus d. So now let's see what is that as d. D is actually infinity, so let's let d go to infinity and see what number we get. First, let's simplify this a little. So this is just negative x times 1 minus d over d minus x. I'm flipping the denominator. And now let's take the limit as d goes to infinity. So what is this expression as d goes to infinity? Let me just write it out here maybe. We have 1 minus d over d minus x. And I'm taking the limit as d goes to infinity. Well, as d goes to infinity, x is fixed, so x and 1 are not going to matter. And as d goes to infinity, these d's are just going to cancel out, and this is going to leave us with negative 1. So this expression is going to go to negative x over negative 1, which is just equal to x as d goes to infinity. So this function, this cross ratio function, is just x, when b is equal to 0, c is equal to 1, and d is infinity, is just the very special function x equals x. It's the identity function. The cross ratio of these guys is just equal to x for any value x. So it's the identity function on the real line. But on the other hand, let's look at the more general case where b, c, and d can be any points, any numbers. If we fix general, distinct values for b, c, and d, then what is the cross ratio function xcbd actually calculating? What is it actually telling us? So to see that, let's let gamma be the unique projectivity from L to itself that takes b, c, and d to 0, 1, and infinity. By the fundamental theorem in one dimension, there's a unique gamma that does that takes b to 0, c to 1, and d to infinity. And that gamma is going to take x somewhere, to some gamma of x. Let's just look at this expression. The cross ratio xcbd, by the invariance of the cross ratio, is just equal to gamma of x, gamma of c, gamma of b, gamma of d. That cross ratio. And gamma of c is 1, gamma of b is 0, gamma of d is infinity. So this is the cross ratio of gamma of x with 1, 0, and infinity. And we've seen that that's just the identity function on this first parameter. So that's just gamma of x. So the cross ratio of x with an arbitrary b, c, and d can be thought of as just the value of x under this unique projectivity gamma that takes b to 0, c to 1, and d to infinity. And let's write it out a bit more explicitly. So we can write out this cross ratio with an explicit algebraic expression for this cross ratio. So by definition, xcbd is just xb over bc divided by xd over dc. And we can write xb is just b minus x, bc is just c minus b, I'm flipping this part so that I can write it as, so that I can multiply by this denominator. So dc is just c minus d, that's what I've written here, and xd is just d minus x. These are all real numbers. So that's what I've written here. So this is the expression I get for the cross ratio of x with an arbitrary b, c, and d. And we can see that indeed this is a linear fractional function. Oops. Sorry. This is indeed a linear fractional function that sends b to 0, c to d, and d to infinity. And one way to see that is just to write it. So it's easy to see that b goes to 0. If we substitute b in for x, we get a 0 here. On the other hand, if we substitute d in for x, we get a 0 in the denominator. So this expression goes to infinity. But what happens if we substitute c in for x? We get b minus c times c minus d on top. On the bottom, we get c minus b times d minus c. And if we multiply the numerator by -1 twice, we can actually get c minus b, multiplying this first term by -1. Second term, we can multiply by -1 to get d minus c. The denominator stays the same, and we see that these cancel out. So this is just 1. So this is, so in some way, what we're calculating is just, what we're calculating under this cross ratio function is just the value of x under this linear fractional function, which sends b to 0, c to 1, and d to infinity. So that's another handy way of thinking of the cross ratio. We can think of reframing our line, our real line, by sending b, c, and d to 0, 1, and infinity. There's a unique way to do that by the fundamental theorem of projective geometry. And so that's a unique kind of way of framing our 3 points, 0, 1, and infinity. And in that framing, where does x go to? Well, it goes to this gamma of x, which is just its cross ratio with b, c, and d. So that's another way of thinking of the cross ratio, another way of interpreting it. And we can visualize the cross ratio explicitly by explicitly constructing the projectivity gamma, which sends b to 0, c to 1, and d to infinity. So here's my line with x with b, c, and d. I've drawn another line, a vertical line here, through 0. And I've put a point, a center of perspectivity here, vertically below d. So as a result, this is going to project d to infinity, because it's parallel to this new line. And I've positioned it along this line in such a way that it projects c to the point 1. And I've also arranged it so these points intersect at 0. So it's going to send 0 to 0. And we can see that that this perspectivity sends x to a gamma of x over here. So for this b, c, and d, the cross ratio of x with those is this gamma of x. We get to explicitly see its cross ratio as this point gamma of x on this line. So it is possible to physically realize or visualize the cross ratio this way, but as you can see, it's also quite complicated. So in some sense, there's no getting around the fact that the cross ratio is slightly bizarre when we try and really understand it geometrically and visualize it. But that said, this slightly more algebraic expression can be very useful. It's just the image of x under the unique linear fractional function, the unique projectivity that sends b to 0, c to 1, and d to infinity.